Today, we're going to go over the steps to solving fatigue problems with mean stress. Now, let's remind ourselves of what mean stress is. If we have a fatigue cycle and the maximum stress is not equal and opposite to the minimum stress, then we're left with a value of mean stress, the average stress between the max and the min. Now, this mean stress could be a positive value, so we could be pulsating in tension, or it could be a negative value, meaning we could have negative mean stresses. But the question is, how do we correct for this mean stress and find a fully reversed stress amplitude that we can then solve for the cycles to failure? So let's walk through the steps. Like any problem that we would do in fatigue, the first step is for us to determine the rotating bending endurance limit of our material. We can use the relationship with the ultimate tensile strength, where it's 50% of the ultimate tensile strength below a certain threshold. Or we can, if the material is in our tables, we could search for this endurance limit from our tables. The next step is to find the actual endurance limit specific to our problem. And that's where we need to introduce endurance limit modification factors called Marin factors to correct for things like the size of our object, the temperature that it's at, its surface finish, and so on. The next step is to look at our geometry. If our geometry includes a notch, which concentrates the stress, then we need to first find the static stress concentration factor, the KT value, and then we need to calculate the fatigue stress concentration factor, KF, using Q, which is our Knox sensitivity factor, or using the square root of A, which is Nueber's constant. Once we've done that, we can then calculate the actual stress amplitude and mean stress, including the effect of the stress concentration. And so stress amplitude, mean stress, max stress, min stress, all of the stresses that are relative to zero are increased by the value of Kf, that fatigue stress concentration factor. Now, we're finally at a point where we have the stresses that are relevant to our geometry. Now we can start to do a series of tests to see if our part has cycles to failure that matter. The first check is to check for yielding. If our part yields, then we stop. If our part is undergoing yielding, that plastic deformation means that we cannot use the stress life approach. We need to use something like strain life, which is a different approach than what we learned in this class. So the first thing we do is to check for yielding, and if yielding is true, we stop here. We say cycles of failure is less than 1,000, use the strain life approach. Now the yield check is simply the Langer yield line equation. And we can include a safety factor, where the safety factor for yielding is equal to the yield strength of the material divided by the maximum stress. This is also equivalent to the yield strength divided by the stress amplitude plus the magnitude of the mean stress, where if our safety factor against yielding is greater than 1, no yielding occurs. And if our safety factor for yielding is less than 1, then yes, yielding will occur in our material. We stop here and we say the strain life approach is required to continue. That is our first check. Now our second check is to check to see if our problem has infinite life, meaning the cycles to failure is greater than 10 to the 6. We have an infinite life design. And this check would require one of our fatigue failure criterion. We've learned about 6 different ones, but let's just focus on a classic example, which is Goodman's equation. Goodman's equation is a linear equation where the safety factor for infinite life is equal to 1 over the inverse of the stress amplitude divided by the endurance limit plus the mean stress divided by the ultimate tensile strength. And this is the case where when mean stresses are greater than 0. In the case where mean stresses are less than 0, then we use the negative mean stress criterion, where the safety factor is equal to the endurance limit divided by the stress amplitude. Now, if NF is greater than 1 or equal to 1, then we have a case of infinite life. And we can stop here and say our design has infinite life, greater than 10 to the 6 cycles. If our safety factor against infinite life is less than 1, then we don't stop here. We can simply state we have a finite life condition. That means we can apply Baskin's equation. Let's move forward in finding the cycles of failure. So now that we've done our 2 checks, we finally get to the point where we can start trying to solve this problem. The first step is to find the equivalent fully reversed stress amplitude for our problem. In essence, what it does is it replaces our state of mean stress and stress amplitude with a state of stress that is fully reversed, an equivalent fully reversed value, so we can use Baskin's equation. So if we know the stress amplitude and the mean stress for our geometry that we've calculated, we plug those values in. We plug in the ultimate tensile strength, and we find a fully reversed stress amplitude, which we can use to find the cycles of failure. The next step is then to find the Baskin constants for our particular geometry. So we need to find the A and the B parameter, which requires us to use our endurance limit, the actual endurance limit of our part, which we found, and the S1000 that we would calculate from that as well. So now with all of our constants for Baskin equation and having a equivalent fully reversed stress, we can finally start to solve problems and find the cycles to failure, where the fully reversed equivalent stress is equal to A times n the cycles to failure to the power B. We can rearrange this equation and solve for the cycles to failure for our equivalent fully reversed state of stress. And this cycles to failure, it matches, or it is equivalent to our case that does have mean stress. Now, if we are determining finite life, and we also want to include a safety factor that's provided to us, we can solve for the cycles to failure incorporating our safety factor by simply dividing that stress amplitude by the safety factor that's given to us. And with that said, it's pretty much the method that we use to find the cycles to failure for fatigue with mean stress.